Welcome to this video on 25CS210 Internet of Things. We will be discussing IoT communication protocols, starting with the network/transport layer protocols like IPv6, 6LoWPAN, and RPL. We will also cover application layer protocols such as COAP, MQTT, and XMPP, which define how data is exchanged between applications. Let's begin by focusing on IPv6, one of the key network/transport layer protocols. First, let's consider the concept of uniqueness. How are you uniquely identified in a large network or institution like KITS? In networking, this unique identification is achieved through an IP address. An IP address is a number used to identify a computer or a network of computers. As a prerequisite for understanding IPv6, we first review IPv4, which is a connectionless protocol featuring address classes like A, B, C, D, and E. IPv4 uses a 32-bit addressing system with dot decimal notation. An IPv4 address is broken down into 4 parts, each representing 8 bits, totaling 32 bits, or 4 bytes, written in dotted decimal notation. A key characteristic of IPv4 is its address format. A 32-bit address written as 4 numbers, called octets, separated by dots, such as 192.168.1.1. Regarding its address space, IPv4 offers approximately 4.3 billion unique addresses, which is 2 to the power of 32. With the current world population exceeding 8.2 billion, the address space of IPv4 is highly constrained. IPv4's function is to provide logical addressing to uniquely identified devices and route data. It is connectionless, making it fast but less reliable than TCP, and it still routes the majority of internet traffic. The main limitation of IPv4 is address exhaustion. The 4.3 billion addresses are insufficient for the rapidly growing number of internet-connected devices. IPv6, its successor, uses 128-bit addresses to provide a much larger address pool, gradually replacing IPv4. IPv6 provides a much larger address space than IPv4, which is essential for billions of IoT devices. Its strengths include 128-bit addressing, built-in security features, and efficient routing. However, the transition from IPv4 is slow, and resource-constrained devices may struggle with the full IPv6 stack. It is the foundation for global IoT addressing. An IPv6 address is 128 bits long, structured into 8 groups of 16 bits separated by colons. This provides a vast number of unique addresses. In summary, IPv4 is 32-bit and uses numeric dot decimal notation, requiring DHCP or manual configuration. IPv6 is 128-bit, uses alphanumeric hexadecimal notation, and supports auto-configuration. The IPv4 header includes fields like version, header length, total length, identification, flags, and checksum. These fields are critical for packet forwarding and processing in IPv4 networks. Comparing the two, IPv4 headers have several fields not present in IPv6, such as identification, flags, fragment offset, and header checksum, contributing to a variable header size. IPv6 streamlines the header for faster processing. Key differences in addressing include IPv4's 32-bit addresses using decimal notation versus IPv6's 128-bit addresses using hexadecimal notation. IPv6 offers a vastly larger address space for future growth. IPv4 supports manual configuration and DHCP, while IPv6 supports SLAAC, DHCPv6, and manual configuration. IPv6 also improves end-to-end connectivity without relying on NAT. IPv6 has built-in IPsec support and performs fragmentation only at the sender, unlike IPv4. IPv6 also uses a flow label for packet flow identification and replaces broadcast communication with multicast and anycast. IPv4 has a variable header size of 20 to 60 bytes and uses address classes A to E. IPv6 has a fixed header size of 40 bytes and does not use address classes, instead relying on prefix-based addressing. IPv6 was developed to address IPv4's problems, such as address shortage and lack of quality of service guarantee. New IPv6 features include an enlarged address space, fixed header format for faster processing, better QoS support, and neighbor discovery. IPv6 offers advantages like faster speeds through multicast instead of broadcast, stronger security with embedded IPsec, and improved routing efficiency. Additional advantages include reliability, being the long-term solution for global network growth, device self-configuration, security support through IPsec, and simple aggregation of prefixes for bandwidth savings.